Welcome to this video of Shearwall Pro, where we are going to talk about how to do the lateral analysis for a very simple two-story building. As you can see, this building is 2 stories and it is very simple. There are no overhangs, there are no building setbacks from one story to another, or anything that would make it complicated at all. It's 4 walls, it's a simple rectangle, 2 stories. For the most part, the shear walls line up from top to bottom. The only complication to this building is what happens at the front wall right here, and really we can get a better look at it. When we look at the front elevation, we can see we have a nice shear wall right here, and directly below it we have a door in the middle of the wall that lines up below it. That is our really only complication for this building. Let's go ahead and take a look at what we've got here. This is the main floor plan, the first floor plan. This is the front right here, the door you walk in, and then this is the second floor plan. You can see that nice 7-foot long shear wall right there. And let's just take a look at what we've got for the building. Here we have a longitudinal cross section. We have the foundation system, the main floor system. Then we have the first floor walls, the second floor system. Then we have the second floor walls and the roof that sits on top of that. And we can see that in a couple of longitudinal cross sections as well. And again, back to our elevation. So let's go ahead and get right into Shearwall Pro and the lateral drawings. So I have already set up the drawings in AutoCAD where we would make the lateral drawings, the shear wall drawings. And what I've done is I've gone through and I have put a shear wall designator and a hold down designator every place where I think a shear wall and a hold down might be. This is what we're going to start out with our initial design and just see what we come up with. This is the second floor, the roof diaphragm, and these are the first floor walls, which we call the second floor diaphragm. So I want to just point that out because it is a little bit confusing. Architects and architectural drawings, this is the first floor plan, and then this is the second floor plan. Well, in an engineering drawing, we take this second floor plan and we call it the roof diaphragm. And as you can see right here, this is the roof diaphragm, and it's the same drawing. So you can see all these interior walls match up with the bathrooms here and the bedrooms at the front and back of the building, and then the stairs. And the reason we look at it like that is it's easier to see if we look at it in a cross section. So these are the first floor walls, the first story walls, and they support the second floor diaphragm for lateral loads. And then on top of that, the second floor walls support the roof diaphragm for lateral loads. So the first floor walls support the second floor diaphragm, and we call the drawing where the first floor walls are at the second floor diaphragm. And then the second floor walls, they support the roof diaphragm. So we call the drawing that has the second floor walls on it, we call that the roof diaphragm. So it's a little bit not intuitive until you kind of have to twist your brain into thinking like that. But once you get it figured out, it makes a whole lot of other things make more sense when you're thinking about how a building is put together and your drawings. So let's get into Shearwall Pro. So here I've already started it with some very basic things. We have our 2-story simple building. We're going to design this for the awesome client, and this building will be built in Portland, Oregon, with a zip code of 97213. In this area, the city of Portland requires a basic wind speed of 98 miles per hour, and we're going to use wind exposure level B for Bravo. So as you can see, I've already gone through the drawings that I've put grids A, B, and 1 and 2. A and B are the longitudinal axis grids, 1 and 2 are the transverse axis grids, and for this first part, I'm just going to put a bunch of things in really fast because we've already gone over how to do all of these in previous videos. We put our grid. We put all of our grid lines in the building data table, and then A and B are longitudinal. 1 and 2 are transverse grids. And just for some quick building dimensions, A and B are 14 feet apart. 1 and 2 are 36 foot 6 apart. So I'm just going to say A is our datum at 0. Then B is 14 feet. 1 is our datum at 0. 2 is 36.5 feet away. Okay, so here's the next thing that I want to point out. In a one-story building, the roof diaphragm is already inserted for you in the roof diaphragm names. And if we come down here to the diaphragm data table, all we see is roof right here. And if we come down to our shear wall input and solution tables, all we see is one level. We can scroll down and it's blank. There's nothing below it. So let's go ahead and put another, let's define another diaphragm. We're going to call it the second. We'll just call it second for second floor. And as you can see, things are already starting to pop up here. This height from ground came in. And if we scroll down here, look at this. Now we have diaphragms called second in the diaphragm data table. And if we come down here, if we scroll down a little further, here is our input table and our solution table for the roof diaphragm. And if we scroll down a little bit further, here is our input table and our solution table for the second floor diaphragm. So we are all set up and ready to go to do the lateral analysis on a two-story building. Now there are some things that we need to consider when we do this. So we're going to enter the diaphragm heights, and these heights are measured from the ground. So let's go back to Revit. Let's take a look at some dimensions. So it says from the ground, but really what it's measuring from is the first floor diaphragm. So in the first floor diaphragm we define as 0. So, and in this building you can see that the first floor walls are 9 feet tall and the second floor walls are 9 feet tall, and we assume that the floor system is more or less a foot tall. So if we add 9 feet plus 1 foot for the floor plus another 9 feet, that gives us a total of 19 feet to the top of the top plate of the second floor wall. So we're going to enter 19 feet right here for the roof diaphragm height. If we go back and we look at the cross section again, the first floor wall is 9 feet tall, plus we add 1 foot for the floor diaphragm, and that gives us a second floor diaphragm height of 10 feet. Okay, now the next piece of information we want to have is our ridge height, and it's at roof ridge height above the eave. I put a dimension in right here, and it's measured as 5 foot 1 3/4. Let's just call it 5 feet for simplicity's sake. Okay, now we already know, we said this before, our longitudinal dimension is 36.5 feet, and our transverse dimension is 14 feet for the building. Now we need to know the main roof rise, and Shearwall Pro needs to know this so that we can calculate some things about the roof. We go to the front elevation, and we can see right here that the roof is an 8 and 12 pitch. So let's go ahead right over here and enter 8 for 8 and 12. All right. The roof gable data. This building is pretty simple because it's just a straight gable data, or the roof is just a straight gable at both ends and there are no dormers. It's very simple. Looking in the longitudinal direction, we have no surface to the left, wall surface in the middle, triangle, and then right of middle is no surface, and then look. So that would be looking in this direction. And then if we look in the transverse direction, we can see that we have roof, roof, roof. So we're going to put that in here. Roof surface, roof surface, roof surface for left, middle, and right. We come down here, and because everything is very, the diaphragms are the same size in both stories, we're going to leave everything in these tables alone. Okay, now let's get into, let's go back to our cross section, and if we look here, it's asking for wall heights. Remember, the wall heights can be different than the story height. In this building here, the wall height for the first floor is 9 feet. The story height is 10 feet because it goes, the story height is counted to the to the diaphragm level. So in this building, we're talking about the roof diaphragm here at this level. The wall height is 9 feet. And it's asking, are we going to use straps or hold downs? And what it's talking about is at the bottom of the shear walls here at the roof diaphragm, are we going to use straps or hold downs to resist the uplift? And because these are walls that are above the concrete foundation, we are going to use straps. Straps connect the bottom of the upper floor walls to the top of the lower floor walls. So straps are story-to-story connections. So we will select straps right here. Okay, let's get right into the design. All right, so we've done this before. I'm just going to cruise through this part really fast. And we'll talk, and I'll go over a quick explanation when I'm done here about what exactly all of this means right here. So if we look at this, this is our roof diaphragm right here. What I've told Shearwall Pro is if we're looking at grid line A, the grid to the left is none. Right here, there are no grid lines to the left because it is the left grid line. And then the grid line to the right, the next grid line to the right that carries load is grid B. So I said grid B right here. And then for grid B, the grid to the left is A and the grid to the right is none. And then, similar story for grids 1 and 2. To the left of 1, there are no grid lines. And then to the right of grid 1 is grid 2. And then similar with grid 2, to the left is grid 1, to the right is no grid lines. Okay, we've got that part all in. And so as we can see, and then if we look down here at our solution table, look at this. These are our maximum between wind and seismic loads. These are our maximum total loads right here to each grid line. So let's go ahead and enter we can see here our wall heights. Since we entered 9 feet right here, Shearwall Pro enters the default is 9 feet right here. You can change this if you want. Sometimes a wall height, one wall can be different than the rest of the wall heights for a given story. And this is the number that Shearwall Pro uses for the overturning and uplift calculations and sizing the straps and hold downs for each individual grid line. So let's enter our shear walls. So for grid line A, if we look right here, we have a 12-foot 9 and a 13-foot 3 shear wall. So I'm going to say 12.75 plus 13.25. And then the shortest shear wall is 12.75. And then I'm just going to enter 7 and 7 for the tributary width for A and B, and then 0 and 0 for the tributary width for 1 and 2, because the roof trusses go left to right across this. All right, and then for grid B, we have a 9-foot shear wall and a 14-foot shear wall. So I'm going to say 9 plus 14. Then our shortest shear wall is 9 feet. And look at this. We're coming up with the solution table. We're coming up with the solution table right down here. And as we can see for grids 1 and 2, for grids A and B, we have type A shear walls, which are 8 at 6 nailing and no hold downs. Look at that. All right, let's get to the transverse shear walls. We can see that for our transverse shear walls, grid 1, we have 2 4-foot walls. So I'm going to enter 2 4-foot walls. The shortest one is 4 feet. And look at that. We know that our nailing is going to be 8 at 6 with number 2 MSTC 40 straps to secure the walls from the second story to the first story. Grid 2, we have 1 7-foot shear wall. So because it's the only shear wall, it is both the sum of the length of the walls and it's the shortest one. We will enter 7 in both situations here, in both places, for the sum of the length and the shortest shear wall. All right, look at that. We have a pretty good solution here for our roof diaphragm. And remember, these are the second floor walls supporting the roof diaphragm above it. Okay, I'm going to pan on over. Now we have our second floor diaphragm. And then I'm going to scroll down in Shearwall Pro. And then our wall height for the second floor, for the first floor walls, the second floor diaphragm is 9 feet again. Because remember, if we come over here, this wall is these walls are 9 feet tall. And then, because these are the walls that sit directly on the concrete foundation, I'm going to choose hold downs. And as you can see, we're ready for hold downs right here. And then we go through the same exercise here in entering what the shear walls are. And now we have assigned the shear walls. So this total maximum load right here is the sum of whatever the story load is at this level plus the total story load above. So if you subtract 914 from this 1978, you're going to know what the story shear is at the second floor level. This is the total right here, because the lateral loads, the shear loads, are additive as you go down the building. All right, let's get into the shear walls. Grid A, as you can see, we have a 36-foot 6 shear wall. So I'm going to enter 36.5 feet for both the total length and the shortest. Okay, and then I'm going to do the same thing here. As you can see, our solution right here, Grid A, first floor, type A shear walls with no hold downs. Now Grid B, we have our same 9-foot and our 14-foot shear walls again. Whoops. Okay, and then 9's our shortest shear wall. Now we look at grids 1 and 2. Grid 1, same as above, we have two 4-foot shear walls. And then Grid 2, remember, this is the front wall of our building. And that is this guy right here. What is going on here? So right here we have a 7-foot shear wall right here, and it has a strap that goes to at the left end of this wall here. And there's also another strap right here that's next to the edge of the window upstairs, and it goes down and it lines up with the framing that's in between the front door and the window right here. So let's take a look and see what all of that. Oh, and then downstairs we have a 3-foot shear wall here, and we have a 3-foot shear wall on either side of the door and window package. Let's take a look and see what all that means to the calculations. So the first thing we're going to do is we're just going to enter the two 3-foot shear walls, and 3 foot's our shortest one. Okay, so now you see we have a solution. So for grid 1, we have type C shear walls. We will change these to type C shear walls and number 10 hold downs. And then for grid 2, let's zoom in a little bit right here. For grid 2, we have our two 3-foot shear walls here and here, and then we have these number 10 hold downs, HDU 11s, that are in these 4 locations on either side of the shear walls. But then we have this 5th one right here in the middle. And remember, this is the wall, or this is the hold down that aligns with, see how I've dimensioned this at 7 feet from the edge of the wall here. That strap is right here above, and so we need to put a hold down in right here to account for that load that's coming from up above. So we have 4 hold downs total for the shear walls, plus 1 more for that load up above that we generated. That's your basic lateral load analysis for a 2-story building. Okay, now that we have completely done the lateral analysis, the calculations, and we have shear wall callouts and hold down callouts in every place that before we did the calculations we thought there might need to be something, let's go ahead and change everything to match, that way the drawings match the calculations. So here we are at the roof diaphragm. For grids A and B, we can see right here that they are type A shear walls with no hold downs. So I'm just going to go through and take all of these hold downs out of grids A and B. They're gone. Now, for grids 1 and 2, we have type A shear walls with number 2 hold downs. The block comes in by default as type A, so we're going to leave those alone, and I've already put the the wall lengths in. So we're just going to change these to number 2s. Okay, we're done at this level. And then let's pan over and scroll down. Grid A, we have type A shear walls and no hold down, so we can get rid of these. Then at grid B, we have type A shear walls and number 6 hold downs. So I am just going to take all of these and change them to number 6. And it should be noted too that I am not using the wall adjacent to the stairs as the shear wall. This section of the wall will be balloon framed, and how to join platform framing with balloon framing is an advanced topic we'll get into in another video. Okay, on to grid 1. We have type C shear walls and number 10 hold downs. So these two I'm going to change to C, and then these change to number 10. On to grid 2. We can see here that grid 2 calls for type D shear walls with number 10 hold downs. So I'm going to go right here, and I am going to change these shear wall callouts to type D. And then I'm going to change these 5 hold down callouts to type 10. And yeah, I said 5 hold downs. There's the 4 you would expect at the ends of the 3-foot shear walls, 1, 2, 3, 4. And then let's take a closer look here. We can see I've put this 7-foot dimension in, and then a hold down at 7 feet away from the corner. Well, why is that there? So if we remember from upstairs, looking at the front elevation, this is one strap, and then we put another strap right here at the end of this 7-foot shear wall that is next to this window, and that framing aligns with the framing in the wall on the first floor that's in between this door and window. So because there's a strap right here and it delivers uplift, we also need to include a hold down at the foundation level to resist that uplift, and that is what that 5th hold down is for. So we have 1, 2, 3, 4 hold downs plus the 5th one from the load above. Okay, at this point we have completed the calculations and we have put all of the shear wall and hold down callouts into the drawings. Now at the foundation level we can make a couple of minor changes. Let's take a look at this corner right here. Typically at an upper story we would put a strap on each side of the corner if they're required. We would put one here and one here. However, at the foundation level, because of the California framing at a corner, you can share hold downs at a corner. So what we're going to do is we'll keep the larger hold down and we will remove the smaller one. And then after I do that, I typically also take this and just kind of rotate it around a little bit. So that way you can see that this hold down is shared between these 2 shear walls at the corner. And if we pan down the screen, we see the same situation occurs at this wall. So I'm going to remove this hold down also, and then I'm just going to rotate this one out a little bit. And now zooming out and taking a look at the entire 2nd floor diaphragm, 1st floor walls, we can see there are no other situations where hold downs share a corner. So we've removed all of the duplicate hold downs. Let's take a look at grid line B. Note that there is a 9-foot shear wall and a 14-foot shear wall, and I did not use the segment in the middle. I chose not to use that middle segment because it will be balloon framed, and that is an advanced topic we'll talk about later in another video. Okay, now we have everything in our drawing. We have all of the shear wall and hold down callouts for both the roof diaphragm / 2nd floor walls and the 2nd floor diaphragm / 1st floor walls. The next thing that we're going to need to do is include the details. So I have already put all of the details in the drawing, and so let's just take a look at each one of them. Detail 1.1, the standard foundation detail. This detail you're going to use in pretty much every drawing. There's also an alternate for a slab on grade and another alternate for a turn down footing included with the detail 1.1. Because this project has number 10 hold downs or larger, it requires the PAB anchor bolts, and the PAB anchor bolts require a larger footing. Anytime you have a PAB anchor bolt, you need to include this detail and then note where that's going to be put on the drawing, which I have not done yet in this one. The shear wall schedule, which describes how to build every shear wall. This project has gable end walls, so we include the gable end wall bracing detail. And there are 6 versions of detail 3.7. They're all the same at the roof level. 3 of them include the floor-to-floor connection and 3 of them do not. If you have a multi-story building, you include the one that has floor-to-floor connection. And then there are a few different options as to what to do at the base here. This building will have post and beam floor system, so we include this one. There are options for slab on grade and options for floor joist. Each one of them is put together just a little bit differently. Okay, now, as we said earlier, there are no special framing conditions like overhangs, cantilevers, anything like that, so that we don't have to include any of those details. So this is a typical shear wall hold down schedule, 8.1. This is the 8.2, which is the strap detail for the floor-to-floor straps. This detail here is for how to install the HDU hold downs. And then these 3 details here are for where to locate the hold down in 3 different locations. At the end of a shear wall at a door opening, you put it just inside the door. At a corner, this is how you build the California framing corner, and then you have 2 options where to put the hold down. And the final one is at a window opening. The window and door openings are very similar. The only difference is you move the hold down to under the window as opposed to inside the wall framing. So at this point, the only thing left to do is to build the drawing sheets. So I'm going to get started doing that. So we will pick the title block 24 by 36 SWP. SWP is Shearwall Pro. I've already taken the M-View window and made it smaller. This is 1/4 of the width, each of these are, and 1/2 the height. And then I zoomed each of these M-View windows. As you can see, I'll click into that and we can look right down here. I zoomed these at 3/16. I decided that a while ago and set this up so that way I would know what size text, hold downs, shear wall callouts, everything else to put in. So then from here, we're just going to copy this. And then we know what scale because we select the text here and we can see this is half text. So I'm going to zoom this at 1/2 inch to the foot. Okay, and I'm just going to go ahead and do all the rest of the details on this first page. Okay, we were not able to fit everything onto one drawing sheet, so what I'm going to do at this point is I'm going to grab all of these and then I'm going to say send to back. That way it puts all these in the back. Taking a look over here at the title block, notice I've already filled it out. I call it 2-story simple building, lateral loads analysis, and I just generally put what goes on here. So at this point, what we're going to do is we're going to double click that. We're going to rename this sheet to S1. Then I'm going to right click this. I'm going to say move or copy. Oh, it popped up on another screen. We're going to create a copy and we're going to move it to the end. And look at that. Another one came up. I'm going to rename that to S2. Now we're on S2, and I'm going to, so remember we left off at the at the detail 3.7. So I'm going to double click in here. That's the last one we put in, so I'm going to zoom in here. This one is one text. I'm just going to finish all this up. Okay, the only thing left to do with both of these drawings is what I always do is I make sure I'm on layer deet-text. So I come all the way up here, change my layer, and then I put lines just, and notice that I chose to leave, I knew I only had 6 details here. Rather than putting 1, 2, 3, 4, 5, 6 and leaving the bottom 2 blank, I chose to leave the right ones blank. It's a style thing. You can kind of do whatever you want to do if you're making the drawing. Okay, now S2 is complete. S1, we need to put some lines. Remember, these lines go on the deet-text layer. Okay, so I'm just going to do a print preview of what this will look like. And as we can see, the line weights and shades and everything else are here. Now, normally also I would remove all these dimensions. I haven't done that yet for this one. We can see things just kind of look like they should here, all with the correct line weights and shading and everything else. As I pan around, you look at the different details. It looks like I got the wrong scale on this one. I'm going to need to go back and double check that. This is one reason for the print preview. Okay, so let's escape a couple of times. Double click in this one. Click on some text. This says one text, and I'm zoomed at 1/2 inch to the foot. So yeah, I did get that one wrong. Look at that. Our drawings are complete for this 2-story simple building Shearwall Pro analysis. For more information, subscribe to our channel, click like on this video, and go to our website at www.shearwallpro.com and sign up for our newsletter where we will send you the latest information about how Shearwall Pro is growing and changing and how it can meet your needs for a lateral analysis. See you in the next video.